Hi students, welcome to Earth and Environmental Science and Module 6 on hazards. This is video number 6 and we're going to be looking at analysing magmas. Our intention for this video is to give you a little bit of an idea about how to account for the different types of magma in each of the volcano types that we've looked at to this point, and to analyse how the composition is related to the explosivity of the eruption. So we're just trying to get a bit of an idea of how we relate magma composition to the nature of volcanic eruptions. Now, in order to be able to do this, the first thing you obviously have to be able to do is to identify differences in volcanoes in terms of the explosivity. So we've talked about explosive and effusive volcanoes, and hopefully you've got a little bit of a picture in your mind now about the difference between these two types of volcanoes. In addition, hopefully you should also be able to describe differences in the composition of the magma for different types of volcanoes. You may already be able to do that at a very sort of surface level. Say one of the critical components is the difference in the silica composition. And so we'll have a look at that. But then there can also be other things that might affect how explosive a magma is. And then finally, to be able to account specifically for the explosivity of volcanoes, we need to have a really good understanding of the range of different types of chemicals that can be present in magma and the effect that they have both within the magma chamber and also as the magma is rising towards the surface. So let's have a little bit of a look at these. So I want to contrast two different locations where we find magma. The first place we want to look at are the mid-ocean ridges. So this is, I guess, magma that's very similar in a lot of ways to the sort of volcano building lava that we see in islands like Hawaii. So these are our effusive, our slow, steady moving magmas. They tend to be controlled by the source materials, so that is the composition of the magma themselves. The upper mantle material has an ultramafic chemistry. You might remember from year 11 we talked about felsic, those really light coloured minerals, and mafic, the darker coloured minerals that we can see in igneous rocks, and then ultramafic's kind of a little bit further down that end, down I guess towards the olivine end of those different chemicals. And so what we're talking about when we're trying to talk about the difference between felsic and mafic is primarily the silica content. And these particular magmas have very low silica content, so less than about 40%. The mantle is also anhydrous, that means it lacks water, and so therefore any magma that's derived from the upper portion of the mantle at these sorts of divergent boundaries or hotspots, if we're talking about Hawaii, will have highly mafic kinds of magma and of course lava as that magma reaches the surface. The other thing is that it contains very few volatiles, and volatiles are going to be one of these things that we need to talk about in a little bit more detail as well, which we'll do when we do a little bit of a compare the pair side by side in a minute. So these are two very important factors that affect how slow and steadily moving these volcanic eruptions can be. And as I mentioned, the same sort of magma chemistry that applies to mid-ocean ridges also applies to hotspot volcanism, like we see in Hawaii, where the magma sources are deep and therefore low in silica content and low in volatility. Now we can contrast that with the sort of volcanic eruptions that we see associated with subduction zones. So now we're not talking about divergent boundaries anymore. Now we're talking about convergent boundaries, two different plates that are coming together, and usually we've got one plate sliding underneath another. So we're not talking here about our classic continent-continent Himalayan kind of formation. We're talking about ocean-ocean, ocean-continent, where those less dense continental plates are rising up above the oceanic plates, creating those very deep subduction zones and also creating some more explosive kinds of magmas. So where we get magmas originating from the partial melting of oceanic lithosphere and also some of the marine sediments that may have deposited on that surface, there we have a more intermediate kind of chemistry in our magma compositions. So now we're shifting the silica content up. We're creating a higher proportion of silica in the magma, and that creates more of a felsic kind of a magma, but it also is going to contain a number of volatiles. The volatiles in particular that we are concerned about or that affect these sorts of eruptions from these sorts of magmas are things like water and carbon dioxide. The higher the silica content, also the higher the viscosity. So it becomes much stickier. Think about the fact that honey is more viscous than water, and it hangs together better, it holds together better. But what that means is that if there is material that's locked up within it, it's harder for it to get out. And so there's that resistance to flow, which is really what viscosity is all about. That high viscosity is that high resistance to flow, that tendency to hold together more. And so therefore, volatiles that are inside of something that's flowing easily can escape more readily. Those that are sort of being held more tightly tend to build up pressure, and then as anything happens when you build up sufficient pressure, you can have an explosion coming as a result of that. So these high volatile compositions increase the internal gas pressure, and that causes gas outbursts that can fragment the magma, that can actually create cracks and spaces in the magma that have been left behind after this sort of kind of explosive activity. The highly explosive magmas or eruptions that are associated with these types of magmas are the source or the cause of the majority of the large-scale explosive eruptions over the last probably 200,000 years. Certainly the big explosive ones that we've been around monitoring and measuring for the last 100 plus years are definitely ones that have been a result of these kinds of magma compositions. So let's compare the pair. We've talked about divergence, where the two plates move apart, the classic mid-ocean ridge situation. These have low silica content, they have high calcium oxide content and high iron contents. They tend to also have a slightly higher magnesium and also tend to be slightly similar or slightly lower in their potassium and sodium oxide compositions. Conversely, when we look at convergent boundaries, those sort of subduction zone volcanism, we get more intermediate silica content, so up to the 50-65%, much higher content of silica than we have in the ones that have been associated with divergent boundaries. We've got an intermediate level, slightly less calcium and slightly less iron in the magma. We also have slightly less magnesium oxide and kind of just a little bit more of those very active metal oxides, the potassium and the sodium. So you can see when we start to pull these things apart, we can start to get a little bit of an idea of the changes in the composition. Now remember, it's probably also worth at this stage recalling the Bowen series, that idea that different types of minerals crystallize out at different temperatures from the magma, and one of the consequences of that is that it can change the mix. It sort of slightly changes the nature of that magma once certain materials, certain minerals have started to crystallize out of the magma. So that too can have an effect on the magma composition. The most important thing, of course, is to remember that these high silica content magmas are more viscous, they resist flow much more, and therefore they are more likely to be explosive. So if you were looking at this comparison, on the left of divergence is where you put your effusive volcanoes, over on the right with convergence is where you're putting your more explosive volcanoes. One little activity I'm going to get you guys to have a look at is Lake Nyos in Cameroon. Now, some years ago, August the 21st in 1986, thousands of cattle and over 1,700 people living near Lake Nyos in Cameroon died within moments of each other. We're going to get you to investigate the link between this disaster and volcanism. Now remember, this kind of concludes the three little mini-series, I guess, we've had about volcanoes and hazards. And we've looked at several potential hazards associated with volcanic activity. So when you're analysing Lake Nyos, you're looking at lava flow, you're looking at ash cloud, you're looking at lahar, and you're also looking at poisonous gas. So keep those things in mind as you go through the activity and see if you can kind of pick up what sort of things might have had such a devastating effect on the population and also on the livestock around this region in Cameroon. Thanks for watching.